Okay, welcome to our final lesson in organic chemistry about organic reactions. So, there are 7 organic reactions. Some of them are a little easier than others. Here we go. The very first is substitution. So, a substitution is where a hydrogen is going to get kicked off of an atom and it is going to be replaced usually with some type of halogen. And we will go from creating a hydrocarbon and instead it will be a halocarbon. And if you know sports, then you know what a substitution is. Even if you just think about, like, if your teacher is absent from school, they send in a substitute and that substitute takes the place of your teacher. So here I have ethane. Remember, 2 carbons single bonded. And let's say I have a chlorine. Remember, chlorine is diatomic, so it comes in 2s. And what's going to happen is we are going to have a reaction where we have a substitution. So hydrogen and chlorine are going to swap places. The chlorine is going to sub in for the hydrogen. So we would wind up getting chloroethane. That would look like this. All of our original hydrogens are there except for the one that gets subbed out. So one of my chlorines would show up here, and then we would have this hydrogen that's circled as a product along with our leftover chlorine. So we would get the halocarbon and we would get HCl, which you may remember is hydrochloric acid, and this is a substitution. You would just identify that one atom got subbed out for another, and that is the gist of a substitution. They can be any size molecule, but typically it's going to be a hydrogen and a halogen swapping places. So the next reaction we have is addition. Okay, so this is an addition where we have some type of multiple bond, either a double or a triple bond. And what happens is that this, we can do it with a halogen that's diatomic. We can do it with oxygen, that's rare. Nitrogen, that's rare. Hydrogen is another common one. So either a halogen or a hydrogen. And what happens is this entire molecule is going to be added where the double bond is, and the double bond is basically going to be subtracted. So in this space here would be the first chlorine, and in this space here would be the second chlorine. So we would actually wind up getting dichloro, what is this, propane? No, butane. This is butane, this has. So the chlorines would go there, like that. And then the rest of this molecule would have hydrogens stuck all over it, the original hydrogens. And really what happens, the gist of this is that the double bond gets reduced down to a single bond. You see over here we have a double bond, and then here we have the single bond. That happens when the chlorines get added. The reason for that is because each carbon can only bond 4 times. And if we were to sit here and count it, up here, this carbon has 4 bonds, and then this carbon here beside it also has 4 bonds. When we add the chlorines, the double bond needs to get broken down into a single bond so that each of our carbons still will only have the 4 bonds. Right there we have 4, and then right here we have 4, and the only way that works is to break down that multiple bond. Now, if we had a triple bond there, we could add 2 sets. So I could add 4 chlorines if I had a triple bond, 1 set to the bottom and then the other set to the top, and then my triple would be reduced all the way down to a single bond. Or if I had a triple bond, I could just add 1 chlorine set, and then I'd have 2 chlorine atoms, and then the triple would be reduced to a double. So we could do that as well. Okay, the next reaction we are looking at is a fermentation reaction. And a fermentation reaction is how we get bread. I'm sure you've eaten a piece of bread before. You notice that there's like tiny little bubbles in it, like air pockets, and that comes from this reaction here. So when bread is made, there's usually a small amount of sugar that's in the bread, and then there is a catalyst used, which typically is yeast, to help make the bread rise. The reason it rises is because this sugar and the catalyst mix together and create these air pockets of carbon dioxide that help the bread or the dough to grow and look like it's getting bigger and rise. This is also the way that drinking alcohol is made. I'm sure none of you know from experience, but beer is a type of alcohol, and that has bubbles in it. It's carbonated like a soda. And ethanol is drinking alcohol. So when they make beer, it's made in a fermentation reaction. There is sugar, there's some yeast in it, and then it rises and it creates the carbon dioxide bubbles. It also creates ethanol, which is the drinking alcohol. Now, the reason that wine does not have bubbles is because it goes through the fermentation reaction. The sugar from grapes has a catalyst thrown in there. I don't remember exactly what the catalyst is. It's not yeast, but they use a catalyst to get it to ferment, and that creates ethanol and carbon dioxide. But wine does not have bubbles in it. The reason for that is because they distill it or boil it to get all of the carbon dioxide to evaporate out. So it would look something like this, where we have sugar, C6H12O6, and we are going to add a catalyst. Usually that is yeast. Biology people would not say catalyst. They would say an enzyme instead, but they mean the same thing. And then this molecule right here is ethanol. And this is carbon dioxide down here. Now, when bread goes into the oven, I mean, it's only making a small amount of ethanol, but as it cooks, the ethanol kind of like evaporates out of it, as does the carbon dioxide. It leaves, like the gas escapes, but it leaves the pocket, and that's why bread has little pockets in it. It comes from the carbon dioxide. So this is a fermentation reaction. You can ferment basically anything with sugar. And this is how it's done. That's the reaction. Okay, the next reaction is called an esterification, where we have some organic acid that is going to have a reaction with an alcohol, another organic molecule, and it is going to create, you guessed it, an ester, and water is typically the byproduct. So it would look something like this, where we have, and I'm not sure that you remember this, so I'll label it for you. This right here with the COOH, this is our acid. That does not look like the word acid. Boop. Oh, goodness gracious. This program is not easy to use. This is the acid, and then this is the alcohol because of this OH group right here. Basically what happens is that we get the H and OH are going to make water. Remember, HOH is the formula for water. So this is going to break apart and make our byproduct of H2O. And then what happens is these other two molecules smush themselves together. So this purple part here and this part here are going to come together and make an ester. So they break off the ends and form water, and then the ends smush together and make an ester. So you may remember that the ester has the interrupting oxygen, which would be this guy right here is our interrupting oxygen. And then we have our double bonded oxygen right here. So these guys together are going to form the ester once the two purple pieces get mushed together. So that's an esterification. You have an acid and an alcohol. They come together and make an ester. Now, these reactions they're not on the reference table. You kind of have to memorize them, but the questions they ask you are not this specific. They're really not too intense of questions that you need to like feel overwhelmed by this. So if I could get a new page from this stinky app, we can move on. Okay, I'm going to pause. So the next reaction that we are looking at is called saponification, where we are going to take a fat, like literally an animal fat. They don't do it this way anymore. Now they do synthetic stuff. But back in the day, they would take animal fat and they would mix it with a strong base, usually sodium hydroxide, but it may even be lye, which is kind of a common name for a strong base. And this is going to form soap. Now, this is a weird one. The reason is that fat is something organic, and then we have an organic result. So this right here, if you like rearrange the letters, it would spell soap. And that's your hint to help you remember this. So what the reaction would look like is that you are going to have fat, which is some gigantic, crazy long carbon chain, usually like 17, 18, or 19 carbons. And that is going to be mixed with a strong base, usually a group 1 base. Sodium hydroxide is super common. And then you are going to get another long carbon chain. And that is going to be soap. And then you can also get glycerin as a product, a byproduct with this, which glycerin is like an oil. So it is in like a lot of beauty products. It's just like a clear oil. In some cases it can be like a moisturizing oil, or it's like crazy thick. You can buy it like in a drugstore, but in some cases you can put it on your skin and it will like protect from something or other. I don't know. It's an ingredient in beauty products. But that is another one. In terms of high school chemistry, you don't need to know the details. You don't need to know the size of this molecule. Just that saponification is a reaction where fat plus a strong base is going to yield soap. As the result, we have just 2 more reactions. Let's see. The next one is polymerization. And if we were doing this in a lab, this is how you make slime. You can string together monomers, which would be a small carbon molecule, and then you are going to use some trigger to get them to link together and then create many polycarbons all strung together. You make just a really long chain, and typically that's how you make plastic. Different number of carbons is going to give you different types of plastic. So you can think of like a plastic shopping bag or a Ziploc bag versus like the plastic that makes this calculator. They are different kinds of plastic, and that's because their strings are they're different. They have different numbers of carbons and then different attachments to them. Plus, another common polymer would be polyester. That is another polymerization, and that makes something a fabric that can actually be used for clothing. So that's a polymerization. What happens with making slime is that glue would be the monomer, and then you use typically like that borax solution. I know that you've seen the YouTube videos on how to make slime. You would take that borax solution or contact solution, which usually is sodium borate, and that is going to help get those glue molecules or those monomers to stick together. And you can actually see it happening. You can like stick your finger in glue and it'll stretch a tiny bit because those molecules are kind of stuck together. But once you add the borax solution or the sodium borate solution, those strings get much longer because all of those molecules are actually bonded to each other. It's just that it hasn't really dried. You're getting the glue to stick before it dries. So that's a polymerization. And then our final and probably most important organic reaction is combustion. This is a fire. You are going to have some type of an organic fuel, and that's going to burn in the presence of oxygen. So I have this candle, and This candle has a lid, obviously, and then if you were to light this candle and then put the lid on top, eventually the wicks would burn out because fire needs oxygen to survive. If there's no, it uses all the oxygen that's in here, and then this lid is preventing any more from getting in, so the fire has to die. So that's where stop, drop, and roll comes from. If you catch on fire, you roll on the floor, and what that does is the fire that's on your body or on your clothes gets smothered, as they say, which means you have removed the oxygen, so the fire has to go out. So here, what you are doing, that's why you don't open the window to let the fire out. You only open the window if it's the only way to get out, because otherwise the fire can get bigger. By letting in more air. Usually not a good idea to do that. You want to snuff it out if you can. So let's say that you have a lighter, like a candle lighter, and this is full of butane. You know what butane is. That is a 4-carbon chain with all single bonds. And what's going to happen is that when you burn this, it needs oxygen. And the byproduct is actually going to be carbon dioxide, which is why they say burning fossil fuels is not good for the planet. It's because it creates carbon dioxide that goes into the atmosphere. And it also actually creates water. Fire creates water, but because the fire is hot, it's coming off as steam. It's not like the fire is going to put itself out. That's all steam. It just immediately evaporates. So this obviously is not a balanced equation, because here I have 2 hydrogens and up here I have 10, but this is the gist of a combustion reaction. If I had no oxygen, if my fire was smothered, then I would not be able to complete this reaction because it wouldn't be balanced. So you can do this with any hydrocarbon fuel. You can do it with butane, which is in a lighter. You can do propane, that's in a barbecue grill. You can do octane, that's gasoline. You can do it with sugar and plenty of other things. It doesn't just have to be an alkane. There are lots of different types of fuels. Different things are going to burn at different temperatures. For instance, this is not going to be as hot as a welding torch, for instance. It's just different things are going to burn at different temperatures. And then we have gasoline, we have diesel fuel, we have jet fuel, we have rocket fuel. All of those things are a little bit different based on the needs of whatever is burning. But this is probably the most important reaction. The most important organic reaction. It's just that we have some type of organic fuel that is going to burn in the presence of oxygen. Major importance. Oxygen is almost never the limiting reagent, simply because oxygen is in the atmosphere. Something that's important to note, it's actually a very good thing that our atmosphere is almost, if not more than 70% nitrogen and only 20-ish% oxygen. And the reason for that is because if the atmosphere had more oxygen in it, it would be almost impossible to put out fires because there would be so much oxygen to supply all of the fires. We're very lucky that we live on Earth with a not so flammable atmosphere. Nitrogen triple bonds to itself, so that's a very strong bond to attempt to break. But that is it for organic reactions. Just to review, there are 7 of them. We have a substitution where one atom gets swapped for another. We have addition where we can take a multiple bond, like a double bond, and reduce it to just a single bond. And we plug in some type of diatomic, usually a halogen or a hydrogen. Then we have a fermentation where we take sugar and some type of catalyst. We create ethanol and carbon dioxide, which is how bread is made. Then we have esterification, which is where an organic acid and an alcohol, the H and the OH break off and make water, and then those 2 leftover pieces bond together and create an ester with a double bonded oxygen and an interrupting oxygen. You can find that general formula on table R. Then we have saponification, where we have a very long carbon chain fat mixed with a strong base to form soap. And then we have a polymerization, where we have a bunch of tiny carbon molecules get linked together, and that's usually how we make plastics. And lastly, we have combustion, where an organic fuel burns in the presence of oxygen to create carbon dioxide and steam, water. So that is all I have for you. If you have any questions, leave a comment. I will do my best to get back to you. And that is all. Bye.